I'll talk about our recent progress on topological 2+1D topological orders. Topological order was first observed in the fractional quantum Hall effect. When studying this fractional quantum Hall effect, people found that their system undergoes phase transitions, but the gate invariance seems to keep the U1 electromagnetic gate invariance. So this is complete to the Landau-Ginzburg symmetry breaking paradigm that second order phase transitions corresponds to several symmetry breaking, but the symmetry seems to preserved to be U1 symmetry gate invariance, and it seems that there's no symmetry breaking, spontaneous symmetry breaking during topological phase transitions. Built on this idea, previous researchers such as Xiaogang Wen proposed the concept of topological orders to describe this phenomenon. Topological orders is well known for its topological robustness. It has two main properties. The first is the topological ground state inertia. It says that between the ground state and the first excited state, there is a finite energy gap, even under the thermodynamic limit. When we take the thermodynamic limit, the gap between the ground state and the first excited state will not be closed. And so the ground state will remain stable because there is a gap between the ground state and the first excited state. And the degeneracy of the ground state is also finite. And it does not depend on the scale of the system. It only depends on the topology of the material we prepare the system. For example, if we prepare the system on the sphere, then the ground state degeneracy is always 1. And if we prepared it on the torus, then the ground state degeneracy is a constant number. Even we take the thermodynamic limit. And if the genius of the system is G, then the ground state degeneracy is K power G. All this number, the ground state degeneracy, only depends on the topology of the system, and do not depend on how we prepare the microscopic details of the material.
I guess you can also make a hypothesis when you have boundaries, right?
Yes, boundaries is another thing that affect the ground state degeneracy, but we do not discuss here.
Here, those formulas apply to abelian annual theory. If you have non-abelian, it's slightly.
No, for non-abelian annual, it's here that express this property.
I think the scale. K is just a number.
Yes, a number.
It's not all.
Yes.
So you say a constant times. It's also very stage.
I think it is true.
It's completely.
Yeah.
In either case, it's completely determined by the fusion rules.
No, this is the ground state inertia, but not the Hilbert space of many anions, infinitely many anions creating. So it only depends on K is the number of anion types, and it does not depend on whether this anion is abelian or non-abelian. Yes. Oh, you say for non-torus. Oh yes, you are correct. Yes, you are correct. Yes, so this is Douglas. Yes, you are correct. It depends on the fusion, but okay. But on the torus, it is always a constant number, and does not
about defect, maybe we can also say that if we add a defect line, the
Yeah.
accuracy can change.
Yes, yes. This is the first property that the ground state inertia on the torus is a constant number and does not depend on the scale of the system. Of course, you're right. If we take a defect or boundary to the system, the ground state inertia will change. But it is still topological and still does not depend on the size of the system. The other property is the anion excitation. It says that the first excitation, first level excitation of the system is classified by different anion types. A finite set of anion types in the system, and these anions, because this is a two-dimensional system, so if we break these anions along the time, it will not behave simply like a boson or a fermion, but provide more complicated phase factor. For example, theta in 0 to 2 pi, A1, A2. We take it brace, and it will give E and IC. A1, A2. This is for abelian anions. While for non-abelian anions, the braiding will propose more complicated braiding properties, and this E and theta will become the unitary matrix. Oh no. Acting on the original state. This property hints that the non-abelian anions A1, A2 exhibit the internal space, just like quark. It has the red, green, and blue color degree of freedom. And if we transform quarks in the system, the quark color will transform, for example, from red to green and etc. This is behaves like the braiding property, that the anions, non-abelian anions may have internal space. And when two non-abelian anions brace with each other, their internal space will undergo the unitary non-abelian transformation. And the transformation will not change the anion types, but only transform the internal space of the anion. This is the original understanding of topological orders with these two properties. And physics, unlike mathematics, they usually want a lattice model or other some model to describe this physical system. And it will be better if we have a lattice model, because because the lattice model is its surface space is finite and is discrete, and we can do many good things on it. For example, we take the wave functions to operate. We take the wave functions or operations on the surface space of the lattice model. And how can we do this? For example, we have a 2D surface. How can we take the lattice model on this surface? Of course, we need the triangulation. Let's split the continuous surface to infinite many triangles. Yes, lattice model on the space, real space. Yes, to each local degree of freedom to this lattice. But for historical reason, we do not take the triangular set lattice. We take its dual. This looks more clear. The lattice dual means that we take each placket as a vertex and each vertex as a placket. You see they are completely the same. We just take the dual of the lattice. Oh? No, it is still simplex lattice. You just take the dual of the lattice shape. For the triangulation, you take each placket as a triangular. But now you take the dual, then each edge is trivalent. This is just a small modification. Yes, each vertex we have 3 legs.
It's not important.
Yes, yes, it is not important. It's honeycomb. It's just a beautiful drawing. And now we come to our first idea. We want to construct a lattice gate theory. Just as a normal lattice gate theory, the basic declaration of the gate field lives on each edge. For example, we can take a group element of a group, but we are talking about topological field theory, so the group must be a finite group. Of course, we can then generalize the group to more complicated algebraic structure. For example, a fusion category. Here, A is the simple object of the fusion category. It is a generalization of the group as the fusion, for group. For groups, we know the group elements multiplication G1, G2 equals G3. While for fusion category, we generalize the group multiplication to the fusion of group of simple objects. It is now no longer just a simple object C, but a direct sum of C. This means that two simple objects in the on the edges A and B can fuse to it's possible to fuse to many different types of simple objects. Yes, fusion coefficient. Yes.
Are you going to assume that an ABC is always 0 or 1, or otherwise you have to listen?
You do not need to assume that NAVC is always 0 or 1.
But then you have to modify your model so that there are degrees of freedom on the vertices.
Yes, you have to increase degree of freedom. But you're right. Here we only choose the NAVC equals 0 or 1 for simplicity. And it can be easy to generate when ABC is larger than 1. But we do not discuss this situation. For a group, if these 3 vertices G1, G2, and this is G2 inverse, G1 inverse, we say these 3 simple objects, these 3 group elements satisfy the fusion rules at this vertex, just like on the triangle G1, G2, G2 inverse, G1 inverse, we say the group element satisfy the trivial holography around this triangle. Triangle. But for fusion categories, we say there is A simple object, this is the B simple object, and this C simple object. If A tensor, B tensor, C, one is just a simple object in this tensor. Then we say A, B, C satisfy the fusion rules.
Here it also looks like you're assuming self.
Yes, self-duality. How can I say? For example, in a group, if the G edge is upward and it takes a G, this configuration is the same as we take you reverse both the A direction and the group elements. And for fusion rules, if yes, A, yes, oh yes.
Just saying, then if this to be 1 on the right hand side, you should probably have C bar.
Yes, you're correct. If we take the both pointing towards the vertex, then it is A tensor, B tensor, C. One is a simple object in this fusion. Or if
I'm just saying if A times B contains C bar, B bar times C contains 1. But I think what you want to say is that NABC is not equal to C. Well, here he's also assuming no, this is correct.
yes, this is quite correct.
Oh,
A, B, C.
ABC is not 0, and you said today you only consider either 0 or 1, then you get 1.
Yes.
The links are oriented. Is
Oh.
there an orientation, an arrow?
Yes, there is an orientation on edges, on links. This is the same as normal gauge group theory. Yes, no, we do not need the require it to be self-dual. If we reverse the direction of the edge, we simultaneously reverse the simple objects on this edge, then the configuration remains unchanged.
So not assuming self-dual, but I think you are assuming for being sure indicators.
Yes, I do not assume self-dual.
Whether there's, he's wanting to identify like reverse the arrow, and we think that for some theories that's ambiguous up to a sign.
Yes.
And so assuming no
Yes. Why I'm so emphasizing the importance of these three vertex size fusion rules is because remember in the lattice gauge theory, perhaps triangular is not good. Along each plaquette, if the product of the 4 A's anti-clockwise G1, G2, G3, and G4 is not the trivial, is not the identity element, group elements, then we say there is a magnetic flux in this plaquette. This is because suppose you have an electron or other fermion or matter field that goes across this that goes around this plaquette and return to the original position. It will transform from psi to u psi. That is not a psi itself. So the holonomy of the matter around, surrounding this plaquette is not trivial. So there is a non-trivial holonomy in this plaquette. It corresponds to a magnetic flux in this plaquette. But now we take the dual of the lattice. So the plaquette now turns to be the vertex. Then if A tensor B tensor C is not does not satisfy the fusion rules, then a matter field surrounding this vertex will exhibit a non-trivial holonomy. For example, if a matter field of psi surrounding this vertex, it will become the U psi. That is not psi. This means that there is a non-trivial magnetic flux or some similar things sitting at this vertex, but this is not true. This is because topological quantum field theory is always flat. We can never expect that there is a magnetic flux or an electric field of the topological gauge field in this system. We must require that for any particle surrounding any vertex or plaquette, it must still be psi, and there is no magnetic flux in this vertex. So the Hilbert space requires that it should not be the tensor product of all A's. No, this is true. It must be a subspace. Yes, a subspace of the tensor product space. Yes, I want to try to show that the vertex must satisfy the fusion rules. This is because the fusion rules the conflicting of the fusion rules corresponds to that there is a magnetic flux on this vertex. This is like there is a magnetic flux in a plaquette in the traditional lattice gauge theory if the 4A's does not satisfy the group multiplication.
The discussion, the flux is defined if you have group element, right?
Yes.
But in general, you have a category, like a fusion category. Then how do we define flux? You generalize the definition.
Yes, this is what I want to show later. But now we just to know that if A tensor B tensor C, and the trivial object, if the trivial simple object is a sub-object of the fusion A tensor B tensor C, then we say there is no flux. Yes.
That's why you are saying it's not a tensor, because after satisfying this condition, it's not.
Yes. And we just at present we just need to know whether there is a magnetic flux on the vertex. If it satisfies this property, there's no magnetic flux, and if not, there is a magnetic flux. And this is no longer a topological quantum field theory, because topological quantum field theory should not have magnetic flux. Yes.
But you're doing the dual to that. Right?
Yes.
Okay.
Yes.
So you're trying to say that on a straight-line model, they do start with a tensor product, but then they input energetic constraints. That's why they end up with this.
Yes.
I agree.
Yes. So this is our requirement of the Hilbert space, that it is no longer a tensor product space of all A's, but it is the subspace that each vertex shall all satisfy the fusion rules. This is a bit different from if you know the Len1's straight model, where it takes the tensor product here space as the total here system. We just constrain the system and require it only has the on each vertex the fusion rules must be satisfied. This will make some difficulties in calculations because the system is no longer tensor product here space. But it satisfies the goal of topological quantum field theory that the theory must be flat. Yes, yes. Next one we want to discuss is the arbitrarity of the triangulation. We know that since this is a topological quantum field theory, the different choice of the triangulation of the 2D surface should not change the property of the topological quantum field. For different triangulation, we know there is a so-called pattern moves that these three types of transformation. Does not change the topology of the surface, but only how we triangulate the 2D surface. This also applies to the lattice gauge theory. The first one is corresponds to remember. We transform the vertical 2y to the horizontal 2y to the vertical 2y. This must transform the vector space of the system because even the lattice shape has changed. So this transformation, we may give the coefficients to the states. The external four tails A, B, C, D is constrained, while the internal tail M transform to N, so N can be summed over. Also, these coefficients A can be arbitrary. It must satisfy some consistent condition. For example, if we go this system around a circle and return to the original shape, the state must be invariant. For example, if we move this to this, each step is just a move of one leg. Yes, and this is to move this edge. And finally, we remove back to this edge. Then this circle each corresponds to a F symbol. And finally, it returns to the original shape. These 5 F symbols must equal when they compose, they must be equal to identity. This is a consistent condition that F must satisfy. We call it the pentagonal equation.
description of the anions is faithful and so on in order to write this?
Yes,
down?
yes, yeah,
Just
yeah. They all correspond to different lattice shapes, but this lattice shape should correspond to the same topological quantum field theory. So this loop must keep the states invariant. And this is the core condition of fusion rules, and it tells us why we need a fusion category rather than a general category. All these properties up to now are the traditional Len 1 string-net model. And now we go further.
So yeah, previous point I'm confused. Wouldn't this work for any monoidal category?
No, we do not need to input a monoidal fusion category. Pardon?
So a fusion category in particular is a monoidal category?
Yes, yes.
And the pentagon condition that you gave is satisfied in any monoidal category?
Yes.
But you want to assume that you have this extra structure and properties of a fusion category?
Yes. The main require is that we need a finite set of simple objects to serve as a basic digital Fudan on each edge. Just propose a very important question, that is how to measure the flux of the system. For example, we have A tensor, B tensor, C. If one is not a simple object in this A tensor, B tensor, C, how can we know which flux is on this vertex? This is impossible in original string-net model because the fusion rules are more flexible than group applications, and their fusion can produce multiple kinds of simple objects, namely multiple kinds of types. So we have to enlarge the Hilbert space. Add more degree of freedom on the system to carry the flux degree of freedom. But before do this, we must know how to give non-trivial flux. Just as I said before, topological quantum field theory is a flat theory, so it itself cannot produce any non-trivial flux. The only way to contribute non-trivial flux is by external matter field. This is just like the traditional electromagnetic field. Electric field is divergence free. Only when we impose external electric charge like electrons, then there is a divergence in the electric field. This is the same as the topological lattice gauge theory. It is naturally has only trivial flux, and only external matter fields produce non-trivial flux to the system. Yes, yes. This is also yes. This also makes sense. The electromagnetic it is a bit different. This is the central spirit of this construction, that we must introduce eternal field to contribute to break the flatness condition and to produce external non-trivial flux. Naturally, in original lattice gauge theory, the external matter field lives on the vertex. So in our theory, the external matter field lives in each placket. Yes, each plaquette has carries a non-trivial representation of the lattice gauge field and produce non-trivial flux. How? It can give a tail connecting to an arbitrary edge of the lattice and produce the non-trivial flux. For example, we consider a group, for example, Z2. We know when the lattice gauge field is Z2, then the matter field is just wait a minute. This can be 0 or 1. And we say this is just a non-trivial flux. If it is 1, contributed by the anion in the plaquette to the magnetic field to break the topological invariance.
Shouldn't you agree with the anions of the group you're putting up here?
Yes. Yes.
There should be an agreement, right?
Yes. This anion, as it produces non-trivial flux, is a doubled anion. It carries both charge and flux. Not like in the electromagnetic field, the electrons only carries charge and does not have a magnetic monopole. If the same particle type may carry different flux and may carry different charge space. Okay. Yes. How can we classify this anion type? It is here the flatness condition. This depends on the Hopkin operator. Just write this. Recall that in traditional gauge theory, the propagating of matter field, I partial minus E. It's not simply the original propagator like this. It includes a coupling between the matter field and the gauge field. This gauge field will transform the internal space of the matter field. This is what happened to our system. Suppose we have have an anion, have a matter field of type J and some internal space, and it transforms to this space. Its internal space must undergo non-trivial transformation due to it crosses a non-trivial magnetic field. And the coefficient is called the Z tensor.
What do you mean by J?
This is a type of the matter field that I will define soon. And this is some internal space. It means that suppose we have an anion in this plaquette. It has the anion type. It carries some flux P and some other degree freedom that will be defined later. And if we want to move it to the right plaquette, the type of the anion must be invariant, but it may provide a different flux in this plaquette. And its internal space may also undergo non-trivial transformation. Everything except the types of the particle may change.
stereo with the if you take the category and
Yes, exactly. Let's consider a group example. Perhaps I should first propose examples. Let's consider the G2 example. Then the anion is either we know is a historical model. And there are 4 types of anions: E, M, and epsilon. 1. The one anion is trivial anion, so it does not carry non-trivial flux or non-trivial charges. So when one anion crosses either the edge, it will simply trivially enter another placket. And if it is pure charging means it does not carry any flux. So it also does not carry flux. But when it crosses an edge and enter another placket, it serves as a representation of the edge. Yes, just like this. Yes.
So I'm wondering what those anions are in terms of notation J, P, and alpha. So what?
Yes, this is the anion type 1.
So let's pick some anion in the topological, and can you tell me what's the J, P, and alpha?
Oh yes, the P is the flux of the anion. So if it is N, then it carries a non-trivial flux 1. Of course, the fusion rules must be satisfied. So if this is 0, then this is 0. And it trivially cross the edge and onto the right of the edge. While if it is epsilon, namely it is a combination of the charge and flux, then it both carries a non-trivial flux and carries a non-trivial charge minus J. Oh, alpha is an other internal space. For example, this comes from if the fusion rules is not commuting. Yes, not beating. Yep.
Then maybe can you tell me the S3?
Yes, S3. That's a good example. We know S3 has a non-trivial representation, the 2-dimensional representation. Yes. How can we call it? For example, we call it tube. Then it carries a differentiation AB. And it crosses an edge, it carries a group element S. And then its internal space must be transformed to D2 S. This is a group acting on the AB. This is the same as quantum QCD. That you.
I thought the reason to describe S3 is to explain what are alpha. Oh, so you say alpha.
Yes, alpha is the label. The internal space label. This is like the quarks RGB color. For example, your red color crossing the such an edge, and it will become a G color. Then this is alpha equals 1, and it becomes beta equals 2. And this is the coefficients of the transformation. For example, in the A3 case, it is the representation of the S graphene on this edge. But how do we calculate these tensors, and how what's the P and what's the alpha?
It's a Wilson line, right? That's what you're trying to describe.
Yeah.
The Wilson loop.
Yes.
Doing the Wilson line.
Yes, exactly. Yes, it is here the flatness condition. I mean, when we move an anion from the left to the right and then move it to the up. it must be equal to we directly move it upward. This is because there is no flux on the vertex. So the deformation must be, you can always do this multiplication. This gives a condition that they must satisfy. Yes. And what you need to do is just to solve this matrix equation to solve all possible types of Z tensors. Then you know how many possible anion types in the system coupled to the matter field. Two algebra? Tube. Yes, it is tube algebra. But tube algebra is a bit later. And I will then tell you why this is a tube. Oh no, the time is over. Yes, let's give another example. A more out of proof example. That is Eisen. We know Eisen have three charts, 1, sigma, and psi. Satisfying sigma square equals 1, O plus psi. So this is a real fusion category, but not a group like Z2 or S3. Then if we solve this equation, we'll find that this Eisen condition have 9 possible anion types. We label them by 1, 1 bar, 1 psi bar, psi 1 bar, psi bar. Sigma 1 bar, sigma psi bar, psi sigma bar, 1 sigma bar. It has a flux 1. It has flux psi, and flux 1. Therefore, both have flux sigma. And the last one is sigma bar. It contains 2 types of flux, 1 and psi. Let's see what this means. First is the 1, 1 bar. It is simple that 1, 1 bar cross any degree of freedom. It is here 1, 1 bar. And the psi bar crossing a degree of freedom. What will happen? The psi bar, if A equals 1 over psi, it will trivially cross the domain wall and does not produce any phase factors. But if A equals sigma, then it will provide a degree of freedom sigma to this system. Minus sigma psi bar. This means that the psi bar carries the representation of the fusion of the Eisen fusion rules. Psi bar 1 equals 1, and psi bar psi equals 1. Psi bar, when it crosses sigma, it gives the minus 1 symbol, just like the S3, the 3 representations of this S3. And another one is 6 sigma bar.
What is the S3? You're doing the Eisen. You have Eisen everywhere.
S3?
You stick back on S3. Oh, right.
Yes, another example. Oh, sorry. If sigma bar cross the trivial edge, of course nothing will happen. Sigma bar 1. When sigma bar 1 crossing the psi edge, it will give the minus sign. Just like what happens to the Z2 or the previous example of psi bar. But when sigma 1 crosses a sigma edge, then something interesting will happen. it will become the single Fudan. Carries a non-trivial flux. This means that crossing the sigma h will transform the internal degree of freedom, the flux degree of freedom of single anion, and transform the flux from 1 to psi. This is another situation compared with the A3, where we only transform the internal space. Just like this. In this case, the flux are all trivial at 1 and does not change. But this condition, in this situation, the internal flux of the anion transform. This is completely a special case of non-abelian fusion category and does not appear in normal group theory.
Out of curiosity, you're using the same anion model for the vertices and for the fluxes.
Yes.
I guess you could use different ones, but then the fluxes has to be a subgroup or something like that, or
yes.
Or is it
yes.
condition?
So you said there are 9 anions in the double net,
Yes.
which is well known. But the part is new to me was that you have sigma
Yes.
If you count those two possibilities, you get 10, but that's not your point. The point is that sigma bar is an anion type, but somehow you care about the internal.
Yes, it has internal space. We know the quantum dimension of single bar is 2.
Yeah.
So this means that it is the direct sum of 1 and psi. If in the yes. So this means that single bar in the topological lattice model, it is the particle with a 2-dimensional internal space, just like a quark carries a 3-dimensional color space. And this internal space will undergo non-trivial transformation when the particle go across the straight lattice gauge field.
And I guess the internal degree of freedom that does not change the surface electron sector. If you make some detection far away from the anion, you don't see that. So
yes, you don't see that.
Technically, that's the same anion type, but you will have some reason to care about the
yes,
fluxes.
yes. The anion type single bar is the only way that we can measure, and the internal degree of freedom 1 and psi or just the gauge degree of freedom, and we can never measure which one it is. But this doesn't mean that it is unphysical. It is physical. It is not physical. I have to just pass the second part and just tell you how to do anion condensation. Anion condensation, it has analogy as the traditional Higgs condensation. Remember the standard model Lagrange. This is a standard model Lagrange. And in the standard model, there is no such thing as a neutrino or electron. There is only a lepton. a left lepton doublet. It has two components. One is a new L and the other is EL. They are not the independent particles, but two gauge degree of freedom of the of the SU2 gauge symmetry, gauge invariance. Where ER is another kind of particle that only couples to the left-handed doublet, but they are not the same particle. And phi is also a complex scalar doublet called the Higgs field. It has a very non-trivial potential that this provides a non-trivial vacuum expectation value of phi. We can always choose a gauge transformation to satisfy this condition, but it has a non-zero vacuum expectation value. So what will lead to this situation? First, look at this condition. The W anion couples with phi anion in such a case. This means that when phi dagger phi has v square over 2 non-zero expectation value, this will give the W, the original SU2 gauge boson, a mass. So the original free gauge boson W A SU2 now becomes a massive W minus or a positive or minus massive boson. They are no longer gauge boson, but just massive vector bosons. So the SU2 symmetry gauge invariance is broken. And it remains U1. That remains unbroken. During this process, what will lead to the other situation results is that since this is no longer a gauge invariance but now a massive vector, the new L and the EL are now cannot regarded as two components of the left-handed doublets, but they should be regarded as two different leptons. Now becomes the new L and EL that couples to the W field. They are no longer doublets, but two completely different fermions. This is what we call the splitting in our language, but not in standard model theory. And another part is this. Phi is phi 1 plus I phi 2, phi 0 plus I phi 3. And when phi has a non-trivial vacuum expectation value, then new L decoupled with EL, while EL dagger couples with ER. With this term. What is this? This is the mass turn of the electron. Then this means that EL and ER, originally they are two distinct fermions, but now they coupled with each other. And it becomes a Dirac fermion, just one electron. This phenomenon, what we call identification, that two different particles are identified now as one particle. This is also what happens to our anion condensation. But now what condenses is not Higgs boson, but anionic boson. For example, the famous Sept condensation. For example, if we have a Hamiltonian, and we add a Sept condensation term to the Hamiltonian, and with the coefficient that drives to infinity, then the Sept anion will condense, meaning that the Sept anion's hopping operator has non-trivial vacuum expectation value, or the new ground state is a coherent state of infinitely many Sept anion among the whole lattice system. Because this lambda is infinity, this term dominates, and the new ground state must be the eigenstate of this Sept anion. What will this lead to? The first is the gapping of sigma degree freedom. Why? Because this sigma couples non-trivially. Oh, sorry, I have erased it. W is the hopping operator or creation operator of the Sept anion. Yes. This Hamiltonian is just a form of, I just want to get a non-zero vacuum expectation value of the creation operator. Yes, when the Sept anion cross a sigma degree freedom, it will give a minor sign. This means that the Sept anion has non-trivial coupling with the sigma gauge degree freedom. So when Sept anion is prohibitive and it's a coherent state, the sigma anion can no longer will obtain a mass of scale lambda. Yes, this is hopping. Yes, the coupling of the matter and the gauge field is by hopping. Yes, and this hopping is non-trivial. We give the minus sign. So this will make the sigma degree freedom to be gapped with mass lambda, just like the W PM vector boson in the standard model get mass. So original the gauge degree freedom, the gauge group, the gauge symmetry, gauge invariance is 1% sigma the acid, but now sigma is gapped, and we only left two free degree freedom 1 and psi. Because Sept when crossing 1 or psi, it is a trivial action, and has no internal degree freedom changing or any phase factor. So the 1 and psi remains free, just like the SU2 tensor U1 to U1. The residual electromagnetic U1's gauge invariance. This is well known as Z2 because psi square equals 1. So we have breaking the icing gauge degree freedom to the Z2 gauge degree freedom, and correspondingly the matter field comes from the doubled icing, the 9 to the doubled Z2, namely the Topological 2. Yes. Yes, exactly. This is exactly what happens, and let's see what happens to the other matter field. The first is fusion. Oh, I have erased it. Remember that we have this term. EL dagger phi ER. When phi becomes have a non-zero vacuum expectation value, it becomes EL dagger ER term, and this becomes the electron. And for example, two anions psi1 bar and 1 psi bar, they are related by fusion with psi bar. And now there is an ocean of infinity coherent number of psi bar. We mean that psi1 bar and 1 psi bar are now no longer distinguishable, and they are identified as one anion. This is called the epsilon in the Torah code. Another case is this sigma sigma 1. When it crosses a sigma degree Fudan, it will become a sigma sigma Fudan. But now the sigma degree Fudan is gapped. So this process is no longer allowed in the child topological phase after anion condensation. So sigma sigma bar is 2 degree Fudan sigma sigma 1 and sigma sigma Fudan becomes topological distinguishable. And this is called the Tori code E, and this is called the Tori code M.
Where are you right now? Are you at sort of section 3?
Yes, the second part.
The second part of section 3.
Yes. And I will. Yes, I will quickly. Oh, I'm sorry about that. On Friday, my corporate Kaixinji will introduce carefully about the. Yes, so I just yes, so I just introduce the motivations. Yes, just let's go through to the CFT factory. There are many different anion condensations in the system. For example, Tori code. We have the fluxon condensation, the fluxon condensation or the Chorian condensation. There are 2 different condensations in the Tori code. What happens to it? For example, we have a Tori code Hamiltonian, and we add charging creation operator to the Hamiltonian. We know the charging degree is WZ is sigma Z. One minus 1. Then this is simply what we know like Sept bar, because we know the anion E, when it crosses degree of freedom of 0, it will do nothing. And when it crosses 1, it will give the minus sign. This means that the 1 degree of freedom will be gapped, and the Z2 is now broken to the trivial group 0. So after the charging condensation, on each edge, we only have 1 degree of freedom. That is the trivial degree of freedom on each edge.
So you're describing, I guess, the condensation of.
Yes.
But then you get some Z2 theory, like some SPT.
Yes.
Theory with a non-trivial surface.
Yes.
How do you, this lattice model, how do you see that surface? So you have Z2 surface.
Yes. You see,
It's based on.
this is just the the coherent state of the infinite many E charge. Yes.
Like a boundary.
Yes, but we do not take the idea of boundary here. We take the concept of anion condensation, the infinite many anion in the 2 plus 1D system. Yes, I can introduce you soon. There are 2 ways to see it. First, we know this is sigma x 1 0 1 1 0, and its corresponding ground state is 1/2 1 1.
Maybe we should discuss that. I mean, it looks like one case for condensed E and the other case for condensed N.
Yes. If we condense E, then each edge carries a trivial simple object of 0. And if we condense M, then it is antiferromagnetic magnetic states that we have equally 0 and 1. Have time. We have a bit time left, so I can just quickly introduce the ideas. You are right that this seems very strange in our construction. That is Sept ball. Sept ball we get the one sigma to 1%, and this WE plus 0, 1 to 0. But what this WM do? This corresponds to a gauge transformation. The main idea is like this. That is what is flat connection. Flat connection, for example, if we have a quark, then a red quark move across a flat connection, it is still a red quark. But this is not a very, what can I say, a very canonical, a natural choice, because you cannot compare the quarks at this place and this place. Is it really red? Perhaps it becomes green, because they are in different positions and have different Hilbert space. You do not know this is still red like this. You can only move this around a circle and return to the original place. Then you can compare the original and the terminal states. This means that when we have a quark of color R, and what it moves to this depends on how you choose the flatness connection field. I mean, we assign with each placket a reference color. For example, this is red, this is green, and this is blue. And then we move this red to this position. If it is still red, we can even say the color of this distance change, because only when we have a reference color at each position of the space time, then we can say whether the color is changed. This is the same as in our lattice model. For example, we have a sigma over 1 anion, and when it crosses sigma, it becomes sigma over psi. This is flexible, and we do not really know whether the internal space of sigma over 1 has changed. We must choose a reference. The reference is the trivial degree of freedom. For example, the one in the acid. Then we see sigma over 1 cross the 1 degree of freedom, and it becomes 1 sigma over 1. Then we can say sigma over 1 is still sigma over 1 in different places. But this choice is not always natural, and it depends on what you fix the gauge. You can optionally choose another types of field. If it satisfies the condition of the trio flux, then if you have a sigma over 1 and cross the wall, it is becomes sigma over psi. Then you can only know is that sigma over 1 cross the trivial edge and becomes another degree of freedom, and you take this as sigma over 1 in this position. But but this x is not arbitrary. What should you choose this x? The first is that it must have trivial transformation, because 1 itself has trivial transformation. Namely, gxxxxxx should equals 1. The transformation must be trivial. Of course, simple objects can never satisfy this condition, because no simple object satisfies GAAAA still equals 1. So we must choose non-simple objects. Namely, we have to choose a composite object. Of course, with some multiplicity. and gives each vertex a coefficient a. To satisfy this condition. This will give a G symbol, but this F supplements the transformation of the G, and there is no longer another G supplement to the right-hand side. Then this new condition A also satisfies the OR role, plays OR completely the same role as the trivial sim object. And it can be taken as another trivial sim object of a new. This is called algebra or Frobenius algebra. It means that if on each edge we carry the Frobenius algebra, then the system can still be regarded as a trivial connection that an anion single bar with some flux crosses the sigma cross the edge carries degree of freedom A. It still becomes the same degree of freedom, although it may change, although the internal space may change when you look it back in the original degree of freedom 111. This A can also satisfy as another degree of freedom. This is what this N do. The J2 has two Frobenius algebras. One is the trivial 0, and another is 0 plus 1. This Frobenius algebra corresponds to the Rev J2 fusion category. This may another way to understand this transformation is via Hadamard gate. And this transformation corresponds to the exactly EM duality. Perhaps it's too quick. Yes. Yes. Yes, this is the basis transformation. Yes. This means that or more physically a new gauge fixing. You choose not 0 as the trivial connection, but 0 plus 1 as the trivial connection. Then the fluxon M now regarded as the charge on E in the new system. This is just a Hadamard gate if you take the calculation.
I had a mark. You just need the 4x4 matrix.
4x4. Oh.
There's a 4x4 matrix where it's 1 at the corners and it swaps the second and third entry.
You mean what is 4x4?
Well, I guess I can ask you.
Okay, we can talk later. But after all, one thing you have to remember is that for any non-trivial anion condensation like this fluxon, we can also choose a new gauge to transform to a pure fluxon like this. This is just a basis transformation that transforms non-trivial things like 1,1 to trivial things like 1, 0. And all these properties are classified by the Frobenius algebra with some coefficients. So what motivates our CFT is a no anion, a multiple anion condensation. We both condense charging and fluxon. What will happen to this? Of course, this is no longer a topological large gauge theory that is invariant under the pattern moves. So it is not. I mean, it is not a RG fixed point. So we must do RG to flow it to a fixed point. What happened to this flowing?
Sorry, so here, so W is a Hopf number.
Yes.
So you're turning on the form both by Hopf numbers for E and for M.
This is for E and this is for M.
At the same, so alpha and beta both.
Yes, both are non-zero. What happens to this term? If alpha is larger than beta, then there are more charging than the fluxon in this system. And if we do the RG, we will profilate more charging than the fluxon. And after we do infinity steps of RG to the fixed point, the fluxon will be buried by the more charges. And then the systems will flow to the pure charging condensation. Of course, when alpha is smaller than beta, then the chargions will be buried by the more fluxons, and the system will then flow to the fluxon condensation. But things get happy when alpha equals beta. At this condition, the charging and the fluxon have the same number when every time we do RG. And we know charging and fluxon have non-trivial braiding. So they are locked by each other. The fluxons, the chargions will not be free because there are many fluxons. And the fluxons will not be free if there are infinitely many chargions. Yes, yes, it is sometimes called a KW duality. This is just because the charging and the fluxon they are equally matched, and one can never suppress another, and this leads to that both charging and fluxon cannot completely condense, and then the topological invariance is broken. And this critical point is called. Yes. Critical. Is perhaps a CFT. Yeah, it's Ising CFT. One way to show it is via topological holography. Yes, yes, 1 plus 1 dimensions. 1 plus 1 quantum CFT. Yes, on boundary. Let's prove it. One is 1, 0, and the other is this. When we sum over them, because they must be equally matched, then what do we get? We get a square 2 plus 1, 1. One way to see it is via strange correlators. Let this set be omega. And we construct another set that is the ground set of Topological. Namely 1, 1. I will quickly stop here. They construct the system via the square lattice. If you don't like square lattice and you still want the trivalent lattice, then it is of this shape, the truncated square lattice. But we do not consider this detail, so we just take the square lattice. And dually, we put each spin as a plaquette. This is different from the anion, but the external spin. It is S1, S2, S3, S4. And this degree of freedom is S1, S2, S2, S3. 3. The spins are put on the plaquettes, and the links record the correlations between these two states. And we know the icing ground state is the tensor product of 0 and 1. Sum over or SI product IJ. Yes. We know this is the ground state of the stringate. Once we choose SI and SJ, we mean that the fusion rules at this point is naturally satisfied, because this is the boundary of the plaquette. And we choose an omega state. This is some tricks. We use E exponent beta 0 and exponent minus beta. And we take their overlap. It is computation. Oh, I want to show this state we construct is the critical lattice model of the IC model. Just see this. When beta equals 1/2 log x squared 1, then omega beta equals omega critical, as I said before, right? Yes. Yes. Okay. Just one step. When we take the overlap, we will get the partition function of the IC model. This is called strange curvature. And this is exactly what we get from the equal sum of the two condensed states. This can be generalized to any other anion condensation. That we have two anion condensation, and we take their equal sum, normalize equal sum, then we immediately get a critical lattice model. And the problem is just to measure this critical model, whether it is first order or second order. When it is second order, what is the CFT corresponds to it? Is the central charge, is primary field, etc. All these things can be done once we get the state. Pardon?
So say instead of C of beta for icing,
yes.
Say it's E of beta with some
yes.
Whatever. And can you write that on the left-hand side by changing the states that you're taking the product of?
This?
Yeah. So if you change the right, does the left change?
I don't know how to change the left. It is just the ground state of the stringate model. Yes, it is. Oh, that sounds. Yes, perhaps you're right. Perhaps this, if we change this set to excited state with certain ribbon operators on the box, then we'll get a defect CFT. Yes, that's a good idea.
Could you go backwards? Like, okay, if you have condensation, you get these CFTs, but
Yes.
From a complex anionic theory to a CFT, let's say, well, a simpler
Yeah.
group, let's say, but could you go backwards? I mean, like, would this give you a mechanism how to construct complex anionic models?
There is some trace to do this, but we do not have a very strict construction. That is the symmetry of the CFT. Is during this condensation, the symmetry of the system is preserved. So the symmetry of the CFT traces some symmetry of the original topological phases. For example, we use C2 to get E and M condensation, and we compute them to get the CFT. So the symmetry of the CFT may be the Z2 symmetry. And this may tell us how to find the corresponding topological phase. But this is not very stable. And yes, we can only find the minimal symmetry.
Okay, so if not, what's next?
Thank you.